Beijing, in northern China. Beneath the surface of this giant city, there's a growing problem. New York-based architect Wendy Fock is investigating the cause of the concern.
Beijing is one of the world's largest cities with over 21 million people, but it's seriously lacking in drinking water. With 100 cubic meters of water per person per year, it's actually one of the most water-scarce cities on the planet. The groundwater is so depleted, it's actually causing subsidence. In some areas of the city, the earth is actually starting to collapse. Rainfall in the city has been decreasing since the 1950s. The problem is only going to get worse. The south of China has a much higher rainfall than the north. So could it be possible to transport water across the country from the south to the north?
Moving enormous quantities of water across one of the world's biggest countries seems impossible. But China is no stranger to ambitious engineering. More than 2,000 years ago, engineers began work on the 20,000-kilometer Great Wall of China to protect against northern invaders. The wall took 200 years to complete and is the longest man-made structure ever built. In 1055, the Chinese built the Liaodi Pagoda. At 84 meters tall, this strategic structure is still the tallest brick pagoda ever.
Phew.
And in the 15th century, the emperor built the Forbidden City. Trafalgar Square could fit within its walls 70 times. And with almost 9,000 rooms, it's the world's largest palace complex. But engineers will need all their skills to complete their latest project. And the culmination of all their expertise is spectacular. The South-to-North Water Diversion project is the largest and most ambitious in the world. Once complete, the entire network will be 4,350 kilometers, more than the distance between New York and LA. 3 routes, eastern, western, and central, will connect rivers from the south to the north of China. It will take up to 50 years to complete. And when finished, the 3 routes will transfer 45 trillion liters of water each year.
I'm so proud to work here because this will supply clean water to millions of people.
In order to realise our plan, we have to solve many technical problems.
Of the 3 routes, the eastern has been completed. The western has yet to be started, and the central is the most challenging. On the central route, the water must flow over 1,400 kilometers, the same distance as Land's End to John O'Groats, entirely by gravity with no pumps. At the start, the Danjangkou reservoir will store 29 trillion liters of water. The 9-kilometer-long Shahur aqueduct will transport water at 380,000 liters per second. It will travel under the Yellow River and arrive 15 days later in Beijing. China's water diversion project is so huge, it takes days to drive it.
I'm following the central route from Danjangkou to Beijing.
Traveling from the south to the north, Wendy will see how this seemingly impossible project is being built.
It's such a huge challenge. How do you move water thousands of kilometers across a whole country? How do you cross mountains, rivers, valleys, and all these types of terrain and keep water flowing downhill? How do you manage the flow of water over such large distances? You need gigantic dams, kilometers of channels, huge aqueducts, and massive tunnels. It's engineering on an epic scale.
China's South-to-North Water Diversion project will move 45 trillion litres of water per year along 3 routes to northern China. The central route stretches over 1,400 kilometres. The water flows at 420,000 litres per second, transported by gravity alone. Wendy's journey along the central route starts in the south, at one of the largest man-made lakes in China, the Danjangkou Reservoir.
It's beautiful here. All this water is traveling about 1,400 kilometers north to Beijing, and that's pretty amazing. Every drop of this water in this reservoir is going to be heading north. So, in order to contain this much water, you need a very big dam.
The original dam has been here since the 1950s, but it's not big enough for this project.
When this dam became part of the South-North Water Diversion project, more water had to be contained. So to do this, they had to raise the dam by 15 meters. Raising a dam is not easy. Old concrete and new concrete are not easy to join.
The dam's location raises the stakes even higher.
There's approximately 700,000 people that live here, so it's vital for the engineers to make sure that the dam does not break.
To find a solution to raise the dam safely, engineers must look to the past.
I'm really excited to see this. This place is part of engineering history, and it's structures like these that make me really excited to be an engineer.
Engineer Dan Dickrell is in the Sierra Nevada mountains in California, USA, to see a construction that could help inspire the engineers in China.
Wow! This is the O'Shaughnessy Dam. It's 131 meters tall, 277 meters along the crest. When it was completed, it was the second biggest dam in the world. Wow, what an amazing view. But the dam wasn't always this high.
The original dam, built in 1923, was only 105 meters tall. The dam created the Hetch Hetchy Reservoir, which provided water to the residents of San Francisco.
But within a year, the project hit a snag. More water was required, which needed the reservoir to become bigger. The only way to do that was to raise the dam. The problem is raising a dam is much more difficult than building a new dam in the first place. This is actually quite impressive. I'm lucky to have access to this space. Only people that maintain this dam are allowed in this place. The problem with raising a dam is you have to put new concrete on top of old concrete. Trying to get it to bind it together, there's a problem because the new concrete will shrink as it cures, as the water leaves that mixture. That shrinkage can cause stress in between the old concrete and the new concrete, creating a poor bond. A second issue, a larger dam allows more water to be stored, but the pressure of that water behind this dam, trying to force its way out, toppling the dam, those forces are tremendous. At the time, a dam had never been raised 26 meters before, so it was a risky issue and something the engineers had to contend with.
Water engineer Michael O'Shaughnessy was determined to build a revolutionary dam that could achieve the impossible.
O'Shaughnessy built the original dam to 105 meters, which was right around here. And I was big, but he was a smart guy and he realized it might need to be bigger in the future. His design needed to be adaptable. So O'Shaughnessy came up with a pioneering design adaptation to his original dam that allowed it to be raised in the future. He put a series of steps, 1.5 meter, almost look like stairs on the dam. What this did is it increased the surface area and enabled the bond between the old concrete and the new concrete to be as strong as possible.
By building a series of giant steps on the original dam, it dramatically increased the surface area, helping the new concrete to stick.
Engineers took O'Shaughnessy's trick of increasing adhesion one step further by scoring and notching the surface of the concrete, allowing for a tighter bond between the new and the old material.
The result is an incredible feat of engineering.
Wow, that is a long way up. That 26-meter dam raise made a big difference. The overall reservoir capacity increased by 75% to an overall volume of over 530 billion liters of water.
Over 80 years since the raising of the dam, it still provides water to the 2.5 million citizens of the San Francisco area. In South China, engineers have achieved the impossible. Danjangkou Dam is 12 times longer than the O'Shaughnessy Dam, but engineers have still been able to raise it by 15 meters.
This is one of the longest dams I've ever seen. This dam is huge, and you could really see the new and the old dam being joined together. It is so big that the whole thing actually feels like it's wrapping all around us. It's amazing. And with the sun setting, it's beautiful. You could really see the new raised bit of the dam, which is nearly 15 meters above the old dam. It is really enormous.
Joining the old and new concrete together was the dam engineer's biggest challenge. And like the O'Shaughnessy Dam, the secret was to increase the bonding area. First, the existing concrete is blasted to make thousands of grooves, which, like the steps on the dam in California, increases the size of the surface. Then thousands of steel rods are drilled into the dam to help anchor the new concrete as it's poured on top. It took 4 years for the dam to reach its new height of 176 meters. But with the volume of water in the reservoir increased by 12 trillion liters, there's a further challenge.
With too much water pressure, the bottom of the dam would erode away and the dam itself would tip over. So, to solve the high water pressure and the base of the dam from eroding, engineers had to install a huge grout curtain on the base of the dam.
A grout curtain prevents the weight of water seeping underneath the dam's base. Waterproof grout is injected beneath the dam. The grout forms a giant underground wall or curtain, 65 meters deep, that holds the soil under the dam in place. The engineers succeeded in raising the dam and filling the reservoir, but this is just the starting point for the water's long journey. From the giant Danjangkou Dam, the water flows entirely by gravity along aqueducts and open channels all the way to Beijing. China's South-to-North Water Diversion project is directing water from the wet south to the parched north. It's the biggest water project the world has ever seen. Architect Wendy Fock is following the central route to see how the engineers will achieve the impossible. Over 1,400 kilometers long, It will carry 18 trillion litres of water to Beijing every year. More than 7 times the annual amount used in New York City. Wendy's travelled 250 kilometres north to one of the most challenging terrains on the route, the Shahur River. The region's heavy rainfall and swollen rivers can cause havoc.
This is the Shahur River. Usually in the rainy season, this is all filled with water. The ground is really soft, so it's often flooded. Shahur also means sandy river.
Seasonal flooding will breach the channels of the diversion project.
Open channels will not work in terrains like this, so engineers had to devise a new way to move the water.
Could the solution to such a challenge lie with engineers thousands of years in the past? Archaeologist Jens Köhler is in Rome, Italy, seeing how this ancient city met its need for water.
For the first 400 years of Rome's history, the city relied on water supply from the Tiber River and from groundwater wells. The city was growing, and these people needed not only space but water.
There was bountiful water in the Apennine Mountains, 100 kilometers away. Could the Romans find a way to move the water to Rome? Roman author Vitruvius wrote about civil engineering and architecture. His work on transporting water was an essential influence for Roman engineers. Incredibly, what they achieved 2,000 years ago is still visible today.
This is the solution of Rome's water problems, the Roman aqueducts. Rome had 11 of these aqueducts.
These enormous structures are up to 91 kilometers long and 33 meters high.
Water comes from the mountains and flows in the water channel towards the city.
One of the oldest aqueducts is the Aqua Marcia.
One can still look into the water channel. The water level was about 2 feet high. This may be 1/3 or half of this. But the Roman water is very hard. It's full of minerals. And you see this here. It accumulated up to something like 20 centimeters.
The Romans also devised a way to ensure there were no leaks.
This is plaster mixed with crushed tiles and crushed pottery. So something what protects water from penetrating. We know that they probably mixed olive oil in to make it even more water resistant.
Roman engineers started building more and more ambitious aqueducts. Aqua Claudia is 69 kilometers long and over 30 meters high. Completed around 47 AD, it took 6 years to build.
This is one of the best parts of the Aqua Claudia. More than 100 arches of massive stone are preserved here.
Like the engineers in China, the Romans had to transport water across challenging terrain, using gravity to keep the water flowing at just the right speed.
Vitruvius recommends as a gradient 0.02%, 20 centimeters on a distance of 1 kilometer. Because fast running water causes turbulences and could damage the aqueduct channel. And fast water streams transport all impurities, pebbles, sand, everything. Did you want to have this in your final fountains in Rome? In your drinking water? No. How could they manage this without modern technology?
To keep the gradient correct, Vitruvius described a leveling device called a corybatis.
You see the plumb lines, and yes, they're both out of level.
The slope can be further checked with water.
I have more water on my right and less on the left. Let me try to level this.
Once the corybatis is level, it's possible to continue the straight line to the next arch position, using the sights and marking it on a vertical pole.
Down with the finger, down, a little bit up, and here we are.
Knowing where level was, the Roman engineers could now build the aqueduct with the correct gradient.
To decide the gradient, now we have to take off something, for example, a centimeter or only a half, depending on the distance.
The same process could be repeated one arch at a time, the entire length of the aqueduct. Using simple tools, the Romans built vast aqueducts at precise gradients with an accuracy almost equal to modern devices. It meant 1 billion litres of water per day reached Rome, the same as New York City today.
We are at Fontana di Trevi, beautiful fountain that is still fed by water through an ancient aqueduct. We can learn from Roman aqueducts. Their simple but efficient construction may help us to resolve several water transport problems today.
Inspired by the Romans, the Chinese are building the largest aqueduct in the world. At 1,200 tons, each section is too big to transport, so they must be made on-site using giant molds.
So right now, we're in front of the biggest mold that makes the aqueducts. It is about 7 meters by 9 meters and 40 meters in length. It's the fastest in situ concrete poured mold in China.
The sections can be built quickly, but they must also be strong enough to withstand the forces of the water.
The shape of the mold is super important. When water flows through it, if it were a square, all the forces would be on the stress points on the corners. However, in this case, it is a U, so that forces are evenly distributed onto the sides.
With the giant U-shaped sections in place, the enormous aqueduct can be filled. The Shahur aqueduct carries 320,000 litres of water a second across the challenging terrain. Like the Roman aqueducts, it's constructed at a precise slope of 0.02%. So the water can run along its length. Site operator Li Chu manages the flow.
We set meters along the route to monitor the change of the flow rate and the volume of the water at any time. We use a centralized control. This remotely controlled system, located in Beijing, can operate 64 curved gates to control the flow rate. Chinese engineers continuously worked hard, innovated and challenged themselves. It took 5 years to make the dream of building the aqueduct come true, and they created a miracle.
The 9-kilometre-long aqueduct can cross the flood-swept area, but the next obstacle on Wendy's route is much harder to overcome. 230 kilometres north of the aqueduct is one of China's biggest rivers.
This is the Yellow River. It is 5,500 kilometers long, and it is the second longest river in China.
Laden with over 1 billion tons of silt and with a highly erratic flow, the Yellow River is too unreliable to supply enough good water to the north. So the South-to-North Diversion project must cross it.
The Yellow River is especially difficult to cross because it wanders its course every year and it really changes a lot. And the central route is gravity-fed. To keep the water flowing downhill, building above is not an option. So engineers had to dig underneath into a tunnel. So digging a very long, very deep tunnel in this very soft ground is a huge engineering challenge.
At the tunnel entrance, it's possible to see the scale of the challenge.
I think it's really amazing that all this water slowly goes under this huge Yellow River. There's an 8-meter drop that goes from the south side to the north side. This keeps the water flowing under gravity.
To ensure the water flows without pumps, the tunnel entrance is higher than the exit. The pressure caused by gravity will push the water under the river and keep pushing it upwards, an amazing 45 meters to the other side. But with pressure inside the tunnel from the force of water and pressure outside the tunnel from the weight of the river, engineers needed a solution to prevent any failures.
It was one of the most difficult parts of the central route to build.
Engineer Hu Jingyue is at the project's crossing point.
The Yellow River Tunnel uses a double lining structure. Let me show you. The outer lining is designed to withstand the outside water pressure, and the inner lining is to withstand the inside water pressure. Between the two linings, there is a drainage blanket, which is about 6 millimeters thick. At the bottom, we set 3 drainage pipes. These will collect all the leaking water and drain it away as soon as possible. This releases the pressure between the two linings.
With the plan for the water pressure in place, construction of the tunnel could begin.
The Yellow River Tunnel took 9 years to build. It was a big challenge.
When the water started to flow to the north, I was very excited and I really wanted to cry.
Having crossed the Yellow River, the water can flow unobstructed to Beijing. China's South-to-North Water Diversion project is the world's largest. It connects the wet south with the dry north. And New York-based architect Wendy Fock is on an incredible journey. She's seeing for herself the scale of this groundbreaking engineering. A dam raised 15 meters to form a reservoir for 29 trillion liters of water. It flows via a 9-kilometer-long aqueduct and a 4-kilometer-long tunnel to reach Beijing 15 days later. Having crossed the mighty Yellow River, engineers are dealing with another challenge.
How do you move water across a country? For most of the central route, it's above ground in huge open channels just like this one.
Along the central route, there are more than 1,000 kilometers of open channels that had to be dug quickly.
But to build a channel as long as this is a huge challenge. That's moving billions of tons of earth. And digging slopes like this is not straightforward.
820 million cubic meters of earth and rock needed to be moved. To find a solution, the engineers need inspiration from one of history's innovators. Crane operator Katie Kelleher is moving soil near Birmingham in the Midlands.
The industrial revolution in the mid-19th century in Britain and America meant we needed a lot more transport links. This led to planning of new railways and new canals.
At the time, these projects could only be dug by hand.
Digging by hand does get the job done, as you can see. The problem is it's really, really slow. The engineers needed to come up with a new way to move earth really fast.
In 1835, civil engineer William Otis was working on a 66-kilometre-long railway in Massachusetts. To help with this back-breaking work, the 22-year-old devised a groundbreaking invention. The steam shovel. This monster machine uses around 1 ton of coal a day to heat over 11,000 litres of water to make steam. The pressure from the steam moves 6 pistons, which drive cables to move the boom and dipper up and down, or turn and propel the machine.
William Otis wanted it to be based around the guy working with a spade. So you can see you've got the beam here and you've got the dipper down here. So it's a bit like an arm. So it's a bit like my arm up to my elbow and my hand coming down into the bucket. So if you think of it a bit like a gentleman digging and working away like that. So this machine actually replaces the work of 30 men.
With the help of owner Graham and furnace man David, Katie's getting a unique chance to operate the steam shovel herself.
You have 3 levers, one to slew it round, you have one to move the bucket up and down, and you also have a boat to release the bucket. Unless you know what you're doing, something like this is very, very difficult. Okay.
Take the weight on the brake.
Yep.
Right, really push it down.
Yep.
Put on your brake.
Yeah.
Slew around.
The way this arm works is like nothing I've ever seen. Pull the rope.
Yeah.
So as you can see, the steam shovel takes a lot of effort to drive. It is not easy at all. It doesn't have any electronics. It's quite hard unless you know what you're doing, and I'd imagine things can go wrong very easily. So I think I'll let the expert Graham show us how it's done properly.
With Graham at the controls, it's time to show what this machine's capable of.
So what we're going to do now is test the accuracy of the steam shovel using this apple.
The aim is to pick up just the apple, with as little soil as possible.
So as you can see, we did pick up quite a bit of soil as well. But for 100 years ago, it's very, very impressive.
William Otis's steam shovel was able to shift 500 tons of earth quickly and accurately. In addition to America's railroads, steam shovels dug some of the world's longest canals, including the 82-kilometre-long Panama Canal. And by the late 19th century, there were hundreds of these amazing machines across America and Britain.
When we think of engineering now, we think of excavators. They're almost everywhere. We owe all these excavators to the brilliant William Otis and his magnificent steam shovel machines.
In China, 5,000 excavators are digging 820 million cubic metres of earth and rock. But the sides of the channel all need to be dug at the same angle to ensure that the concrete facing on top won't crack. So some of the excavators are equipped with cutting-edge technology, far beyond anything Otis could have imagined. Site manager Jörg Schittenhelm oversees the new breed, the laser-guided excavator.
Over here on the machine we have the laser receiver that catches the laser signal from the laser transmitter. In addition to that, you got the inclination sensors that are mounted on each moving part of the excavator. So this one measures the opening and closing of the bucket. This one measures the tilt. And of course, on all the other moving elements, like the two arms that we have over here, you got another sensor measuring the movement of the arms.
The apple test can be repeated to see if the laser-guided digger can pick up the apple with more precision than the steam shovel.
There we go. The apple is in the bucket and as less soil as possible is there.
The excavators are extremely accurate, but in China, they must repeat the same maneuvers again and again. This time, the apple test is more challenging.
Next, we're gonna test the accuracy of the system, and for that, we're gonna put this apple on the ground, put the excavator bucket on top of it, turn the excavator 360 degrees, and see if we hit the target level again. Perfect.
With the start position measured and memorized, the test can begin.
All right, there we go. Down to the centimeter, right on spot on top of the apple.
This laser-guided technology is invaluable for the 1,000-kilometer-long open channel.
So what we see is over here is just a slope that we just built, and you can see it's really perfect as it was planned to be. And without a laser-assisted excavator system, this would be almost impossible to build in this quality over such a long area. This is one of the most interesting and challenging products that I've ever worked on. And the China project has been one of the most interesting projects that our system were ever used on.
Engineer Wang Xiaoming looks after the Jiaozuo open channel.
During the construction, we used a lot of innovations and newly designed machines, which improved the efficiency of our construction. Because the excavator has a track, that means it can pass through the muddy land and the slope of our canal, so it's very powerful. Secondly, it is flexible. It can move forwards and backwards and rotate 360 degrees quickly, which also ensures that it has a high efficiency. Thirdly, it has a powerful bucket, which can scoop up 1 to 2 cubic meters in one go.
Excavated with laser precision, the 1,000-kilometer open channel could be dug 30% faster. But some sections need further urgent treatment before the water can start to flow. Engineer Cheng De-Hua has been looking at the problem.
The central route of the South-to-North Water Diversion project will pass through more than 380 kilometers of expansive soil.
This clay-ridden section of soil expands as it gets wet and shrinks as it dries. This movement could cause the channel to crack.
The solution we used was to add 5% cement to the weak expansive soil, which completely changes its features.
Having stabilized the expansive soil, engineers could apply the finish to the open channel.
The operation in the past 5 years shows the treatment works well.
As the central route finally reaches Beijing, the water must travel under one of the busiest cities in the world. Deputy Chief Engineer Wang Lei oversees the route.
The underground construction is very complex. There are railway bridges, highway bridges, and rivers. The distance between the bridge piles and our tunnel is as little as 1 meter in places. In the past 3 years, the citizens of Beijing weren't affected at all. They didn't even notice that there was such a massive project being constructed under the roads and subways they use every day.
The water from the central route has finally arrived at the Tuangchang Reservoir in Beijing.
After a 15-day journey, the water transferred by the South-to-North Water Diversion project is flowing to us from this opening.
Flowing entirely by gravity across China, along the largest aqueduct on the planet, through the colossal Yellow River Tunnel, and along a 1,000-kilometer open channel. Wendy's engineering quest is complete.
The water has made it to Beijing. It traveled from the south to the north of China. 70% of Beijing's water comes from the water diversion project. It's an engineering marvel. It's one of the largest water diversion projects in the world. It's amazing how the engineers were able to design open channels, aqueducts, and tunnels. The South-North Water Diversion project is truly one of the most amazing engineering projects that I've ever seen.
The Danjangkou Dam and reservoir hold 29 trillion litres of water. The water flows by gravity for 1,400 kilometres, from the south to the north of China. The 9-kilometre-long Shahur aqueduct will transport water at 380,000 litres per second. At the Yellow River, the water travels along a 4-kilometre-long tunnel before reaching Beijing. This water diversion project is the latest in China's long history of engineering achievements.
I feel this project is magnificent. I'm very proud to be a part of it.
Seeing this clear river flowing to Beijing, it means the city can enjoy fresh water. I'm so pleased.
Wow! By drawing on the innovators of the past, the many challenges have been overcome.
I think that this is the most magnificent water diversion project on Earth. It took us many years to build, but it will benefit our citizens for thousands of years.
I'm incredibly honoured to be part of the South-to-North Water Diversion project.
The engineers at the South-to-North Water Diversion project have succeeded in making the impossible possible.